Video number 5, lesson 3.2, is on graphing logarithmic functions. Without the use of a calculator, we should be able to graph these without a great deal of difficulty. We're going to rely on what we already know about exponential functions to help us do this. So we're going to sketch and analyze the graph of each function. We're going to describe its domain, range, x-intercepts, asymptotes, and behavior, and where the function is increasing or decreasing. So I'll put that away, and we're going to first look at how do we graph h of x equals log of base 2 of x. What I would like to do, and what I choose to do, is I change this into an exponential. So rather than graphing the log of base 2 of x, the log of base 2 of x can be written as 2 to the x equals y. I'm going to graph its inverse and then think about switching the ordered pairs. So this is easier for me to think of. First, graph the related exponential function, which, if I do the ordered pairs x and y, negative 1, 0, 1, is going to give me a half, 1, and 0. So then if I'm going to graph the logarithm function, which is the inverse, so on this one I'm going to go h of x equals log base 2 of x. Well, since I know it's the inverse, it's half, negative 1, 1, 0, and 0, 1. So that's what I'm actually going to graph. So to do that, I'm going to go to half and negative 1. So halfway and a negative 1, we go 1, 0. And I think this was a miscue right there. If I put in 1, we get a 2, so then I switch the ordered pair around and I get 2 comma 1. So 2 comma 1. So we know it's going to have a vertical asymptote at y equals 0. We're going to sketch our graph the best as we can, going through our ordered pairs, getting close to the y-axis with our vertical asymptote. Okay, so my first thought is to try to graph it as an exponential, then switch the ordered pairs around and graph the inverse. So the domain. The domain on the red graph would be, can't cross the vertical axis, so that means all real numbers that are greater than or equal to 0. So whether you put it as interval notation or if you want to put it in another form, it's not that big a deal. One way to write it is the domain is all positive real numbers. Again, we have the option of saying it's anywhere from 0 to infinity using interval notation. The range. What are the outputs? Well, if you look at the outputs go towards negative infinity, and eventually these would be going towards positive infinity. So we have all real numbers, or again, from a negative infinity to a positive infinity, interval notation. What are the intercepts? Well, the x-intercept. The x-intercept on this graphic crosses the ordered pair at 1, comma 0. The y-intercept, it never can touch the y-axis, so it is none. And now the asymptotes. The horizontal, there is none. The vertical asymptote is when x equals 0. The end behavior, well, how about the limit as x approaches a positive infinity? As x approaches positive infinity, our y's are going to approach positive infinity. And how about the limit as x approaches a negative infinity? Well, x can never approach a negative infinity, so that means as we approach, at best we can do is approach 0. And what we put on that, since we really don't have an end behavior towards the graph, we can leave that one as an omission, or there is none. So the limit as x approaches negative infinity, x doesn't approach negative infinity. The only thing that we could do and make sense of, what is the limit as x approaches 0? And as x approaches 0, then we could say, at least have something to talk about, then it would go towards negative infinity, because that's really what's going on. But it's hard to talk about its end behavior, because typically, as we say end behavior, we want to know what happens when x's approach negative infinity, and that's not happening in this case. It never is allowed to do that. So look at our graph, and is it increasing? You bet. It's increasing on the entire domain from 0 to infinity. And is it ever decreasing? Nope. So what interval? None. So that's our first graph. When I clear that off, we'll go to our second graph. We have the logarithmic function of log of 1/3 of x. So what I want to do is first translate that into an exponential function. So to me, I would like to graph this as y equals 1/3 raised to the x. I'm just changing it from a logarithm to an exponential. So if you think of this, y equals log of the 1/3 of x. In order to find the inverses, the true inverses, I'd have to switch the roles of x and y. Log of 1/3 y, and then I'm going to rewrite this in terms of an exponent. And in terms of an exponent, we have to have an exponent of base 1/3 logs always equal exponents, so raised to the 1/3, or 1/3 raised to the x equals y. And I kind of brushed by that in the first example, and as I thought about it, I probably should have talked about that as we did it, but that's what I'm doing. I'm going to actually find the inverse function by changing the roles of x and y, and then I'm going to solve for y. And to solve for y, what I'm doing is I'm taking this and rewriting it in an exponential format. So that part of it is pretty simple to do. It's just that you got to be shown how to do that and know how to do that efficiently. So now we're going to look at x and y values. Put in our traditional 0, 1, and -1. You put in -1, this becomes a 3. You put in a 0, it's still a 1. And 1/3 to the 1 is 1/3. So what we have is an exponential decay graph. So it's the order pair -1, 3. So do the best to approximate -1, 3. We have the order pair 0, 1, which is in here. We have the order pair 1, 1/3, which is here. We know we have this horizontal asymptote that comes along here for our exponential decay. It goes from high to low. Should never touch, but should get closer and closer to that horizontal asymptote. So in order to graph the inverse functions, we simply turn these two order pairs around. So instead of -1, 3, we graph 3, -1, which is approximately in here. Instead of graphing the order pair 0, 1, I graph 1, 0, which is right here. Instead of graphing the order pair 1, 1/3, we go 1/3 and then up 1. Okay, and now we should have a vertical asymptote that comes along the y-axis, because that's going to get flipped as well. So it's going to come from here and then go up towards your vertical asymptote. So that is the graph of your log of base 1/3 of x. So let's describe its domain. The domain is going to be the set of all positive real numbers. The range is all real numbers. The x-intercept, well, the x-intercept is still the order pair 1, 0. The y-intercept, there is no y-intercept. The asymptotes, there's a vertical asymptote, but no horizontal, so no horizontal. But the vertical is when x equals 0. The end behavior, what happens to our function as x goes to positive infinity, and that is it approaches a negative infinity. And as I said last time, this really doesn't have any place since x never does go towards a negative infinity. So our graph is increasing nowhere, so none. There's no interval on which it's increasing. It's always decreasing. It's always on the downhill slide, so it's from, well, I guess I go from 0 to infinity here. So on the interval from 0 to infinity, it is decreasing. So a couple of examples of sketching a graph and talking about its behaviors on the graph.